I am going to start a new chapter called Factorization. Well, this chapter is there in lower classes too, but in lower classes we use algebraic formula such as square and cube of binomial and trinomials, etc. But here in the class 10 portion, the content is completely different. Here in this chapter we use two theorems, remainder theorem and factor theorem. Remainder theorem lets us know the remainder obtained when one expression is divided by another, and factor theorem lets us know whether a given expression is a factor of the given polynomial or not. And all these are done without performing actual division process. So here we start the chapter. Let's start with a very simple example of division. Here a polynomial is divided by a simple algebraic expression in which the dividend is x cube plus 4x square minus 7x plus 9 and the divisor is x plus 2. This division process you would have performed many times in lower classes, so you don't need any explanation, as I believe. Hence, let's proceed and see what result is obtained through this division process. In this division process, the quotient obtained is x square plus 2x minus 11 and the remainder obtained is 31. Let's try to understand this complete division process in terms of degree of the expressions. In this division, the degree of the divisor is 1 and the degree of dividend is 3. And after the division, the degree of the quotient obtained is 2 and the degree of the remainder obtained is 0. Let's observe here something very important. We find here if the degree of the divisor is 1, then the degree of remainder obtained is 0. So the major observation here is the degree of remainder obtained is always less than the degree of the divisor. And since the degree of remainder is 0, hence the remainder is a constant term. Now let's observe the solution of the same question in a different way. Here the value of the dividend taken is same as above and the divisor too. Here the dividend is x cube plus 4x square minus 7x plus 9. Here we try to split all the terms of the dividend except the first one. Since we know that the divisor is x plus 2, hence we try to find out the partner for x cube such that this pair returns a factor x plus 2. And through a very simple calculation, we can understand that the value needed for x cube is plus 2x square. Now we can say that this plus 2x square is obtained by splitting plus 4x square, out of which the first value is plus 2x square and the remaining value is plus 4x square minus 2x square, and that is plus 2x square again. Now we try to make second pair as we did the first one. For the second pair, we need a partner for plus 2x square such that this pair too returns the same factor x plus 2, and we find that the pair needs a partner plus 4x, and this plus 4x is obtained by splitting minus 7x. Hence, minus 7x is splitted in two parts, out of which the first one is plus 4x and the remaining one is minus 11x. Now we go for the third pair. For the third pair, we need a partner for minus 11x, and we find that the partner needed for minus 11x is minus 22, and this minus 22 is obtained by splitting plus 9, the last term of the dividend. So plus 9 is splitted in two parts, out of which the first one is minus 22 and the second one is plus 31. Now let's observe the third row. In the third row, we find that three pairs are generated. The first pair is x cube plus 2x square. The second pair is plus 2x square plus 4x, and the third pair is minus 11x minus 22, and at last we find that plus 31 is left alone. Now let's observe the next row. Here it's very much clear that the first pair returns a factor x plus 2 after taking common x square. The second pair again returns the same factor x plus 2 by taking common plus 2x, and the third and last pair returns the same factor x plus 2 by taking minus 11 as common, and the last and unpaired element plus 31 is left alone, and that is going to be the remainder in this process. Now let's observe the next two lines. In the first one, we find that four terms are there, out of which first three terms return the factor x plus 2, and the last one plus 31 is remainder, and that you can understand very easily from the second line, and that line is x plus 2 multiplied by x square plus 2x minus 11, and then at last the constant term is plus 31. Now it is clear that this expression is in the form of divisor multiplied by quotient plus remainder, out of which x plus 2 is the divisor, x square plus 2x minus 11 is the quotient obtained, and plus 31 is the remainder. Let's observe now another process for the same question. According to division rule, dividend is equal to divisor into quotient plus remainder. Hence in the next line, the value of dividend is placed and the value of divisor is placed, and quotient and remainder we don't know, that we have to find out through this process. And towards solution, my aim is to make the first term of the right hand side 0, so that at the right hand side only remainder survives. For that we need to replace x with a constant, and observe here the explanation put in yellow shaded box. To make the divisor x plus 2 0, I need to replace x with minus 2 because other change we cannot do. Here quotient and remainder we don't know. So we have to make x plus 2 0, so that the complete first term of RHS becomes 0 and only remainder survive. So in the next step we replace x with minus 2 and we simplify the expression, and at last we get the value of R 31. Hence it shows that the remainder obtained is 31. So overall, in the second method we found that without performing actual division process we found out quotient and remainder, and in the third method we replaced x with minus 2 and simplified, and finally we found that the value of R becomes 31. It shows that the remainder is 31. But quotient here we cannot find out. My main aim is to understand remainder theorem, so I explained this process, and try to understand this third process very well, because this is the key for remainder theorem. So here we start remainder theorem. Let's see what remainder theorem says. Here the statement is, if fx is an expression in terms of x which is being treated as a dividend here, when it is divided by x minus a, the remainder obtained is equal to fa. It means whatever is the value of fa, or whatever value we get of fa during simplification, that becomes the remainder. Let's see the proof for the theorem. Here the dividend is named as fx because this expression depends upon the value of x. Quotient is named as qx because this also is an expression which is in terms of x, and the divisor is x minus a, which is a linear expression in terms of x. It means its degree is 1. Now let's observe the next block. Again, by division rule, we know dividend is equal to divisor multiplied by quotient plus remainder, where dividend is a function on x and it is named as fx. Quotient is another function of x which is named as qx, and x minus a is divisor. And here you see the remainder is written as r, because we know that the degree of the divisor is 1, hence the degree of remainder is 0. So remainder is a constant term and it is not a function in terms of x. Here again the same process we follow what we did in the last method of the previous question. We had to make this value 0 so that only r survives at the right hand side, and for that we had to replace x with x with plus a, because x minus a has to be 0, hence x equal to plus a. It means in this equation all x are replaced with plus a. So in the equation all x are replaced with plus a and simplified, and finally we found that the value that survives at the right hand side is R and at the left hand side it is FA. It means a function on A. It means we find out the value of FA by replacing x with A in the expression that is dividend, and whatever value we get, that is the remainder. Hence, it's proved that if fx is divided by x minus a, the remainder obtained is given by f of a. Now, let's take some examples and we solve it and find out the remainder with the help of remainder theorem. The first example is to divide the polynomial. Here again we recall that relation, that is dividend is equal to divisor multiplied by quotient plus remainder, but we don't write here. We take the advantage of that, we implement that, but we don't need to write all this, and we simply put the reason. The reason is by remainder theorem. So in that relation too we have to aim the same thing, to make the divisor x minus 2 0, so that the term divisor multiplied by quotient becomes 0 and the remainder only survives at the right hand side. So that should be there in your mind, but we don't need to write here because we put the reference of remainder theorem as reason here. Hence we find, to make x minus 2 0, x is to be replaced with 2 in the whole relation or equation, and that is being done and shown here. You can observe here in the red box, all the x in the equation are replaced with 2. Sorry, here there is no equation. The theorem says that remainder obtained is f of 2 if the given polynomial is divided by x minus 2. So in that polynomial, we replace each x with 2 and simplify the expression, and then we get the remainder minus 3. Now let's take another example, example number 2. This 2 is almost same, but I'm taking some more examples so that you understand how to use the theorem and how to write the statements towards solution. Here we find that the dividend is 2x cube plus 7x square plus 14x plus 3, and the divisor is x plus 2. Here too the process is same. To make x plus 2 0 in that uniform equation, so that the right hand side becomes 0 but r survives, and this way we can find out the value of r. So here to make x plus 2 0, we need to replace x with minus 2. So according to the theorem, it's very much clear that fx when divided by x plus 2, the remainder obtained is given by the expression f of minus 2. So now we replace all x with minus 2 in the value given by fx, and we simplify that, and we find that the remainder obtained is minus 7. So this example is over. Let's take one more example, example number 3, where the divisor is 2x minus 3. Now to make 2x minus 3 0, we need to replace x with 3 by 2 in the given dividend, which is named as fx here again, and the same process is continued as is done in above example. So in fx we replace each x with 3 by 2 and we simplify the expression, and finally we get result, and that result occurred is 2. and this too is the remainder obtained when this division is performed. So here, with the help of remainder theorem, in all these above examples, without performing actual division process, the remainder we can find out easily with the help of remainder theorem. Now, at the bottom, you observe, try your self block is there. 3 questions are mentioned here, and all these 3 questions you try at home and find out what remainder you get. And then that remainder obtained by using remainder theorem, you can verify with the division process. But that is for your own satisfaction. Our syllabus says that whatever you do in this chapter has to be done using remainder theorem or factor theorem. The factor theorem I'm taking next. In this video, I covered remainder theorem of the chapter Factorization, and I believe that you could have understood the theorem, its proof, and how to implement the theorem in your solution for different questions very well. In the next video, I'll discuss about factor theorem of the same chapter. If you have any doubt, any query, you can put in the comment box. Thank you.